So, in this module we will discuss some of the fundamentals of the ceramics processing. So, in one of the earlier modules I have discussed that how metals can be processed, particularly metallic biomaterials. So, the word ceramic essentially is derived from the Greek word called keramikos, that is burnt stuff, and in general the ceramics are so in general ceramics are defined as a class of as a class of inorganic non-metallic materials having ionic and covalent bonding and typically processed or used at high temperature. So, this is that typical conventional powder metallurgical based processing of the ceramics. So, you start with the powders first. So, it is a powders, then you mix with some additives or you mix two different kind of powders of two different chemistry, then you do this is called compaction stage. So, this is first is the powder blending, then is that compaction, then you get this kind of small cylindrical shaped green body, that is green, this is called green compact, and this green compact once you put it, once you throw it into a furnace, then you heat it up at high temperature, then green compact it becomes densified. So, this is the process called sintering. Now, sintering is always to be done at a temperature where T by T is greater than 0.5 Tm. So, that means our T by Tm is greater than 1 by 2. So, one of the important process of the sintering is that how you can make these powders, that what I said. So, I will just give you an example of that how these hydroxyapatite powders, because why hydroxyapatite? Because hydroxyapatite again I recall that hydroxyapatite is the inorganic constituent of the natural bone. So, therefore, hydroxyapatite powders how it is synthesized I have mentioned. So, this is called suspension precipitation route. So, calcium oxide you add calcium oxide is added to a orthophosphoric acid solution, and this orthophosphoric acid then it is precipitates, this what it precipitates is the Ca10PO4/6OH2, that is the stoichiometric hydroxyapatite. I may like to mention here also that in the bone that calcium phosphate or calcium apatite that is there, it may not be having all the places that stoichiometric hydroxyapatite. In most cases that hydroxyapatite is present in natural bone in non-stoichiometric hydroxyapatite. Now, once you make this hydroxyapatite, then you can make this hydroxyapatite, you can sinter them with added with certain other metals or ceramics, and then you get a powder mix, and this powder mix you make a compaction, and then you sinter them at high temperature, different temperature in air. So, this is that entire thing that has been mentioned. So, hydroxide powder synthesis. So, this is just to start with the calcium oxide powder, then you disperse them in water, then you stir it in the magnetic stirrer, then you drop by drop you just add this hydroxyapatite. So, and after that you keep at least 1 day for precipitation filtration. After that you dry these hydroxyapatite powders, after you dry you break the agglomerate, then you calcine it in a furnace. After you furnace it, then you add certain second phase, then you make the compaction die pressing, and after the die pressing it goes to sintering furnace again. So, this total circle of the making the synthesizing the hydroxyapatite powder to go to a sintered pellets, this it is a quite a lengthy process, but at each step one has to do additional characterization, like one has to see that what is the particle shape and size using scanning electron microscope, one has to also quantify that what is the size distribution using that particle size distribution like laser particle size analyzer and so on. So, this is that scanning electron microscope picture of the hydroxyapatite powders, and what you see this is the spherical shaped powders, and the spherical shaped powders in that inductively coupled plasma auxiliary electron spectroscopy analysis also can be performed just to see what is the Ca by P ratio, and this Ca by P ratio is very important in case of hydroxyapatite because that actually influences biomineralization property of many of these hydroxyapatite based composites. Now, in that stoichiometric hydroxyapatite when with the composition Ca10PO4/6OH2 their Ca by P ratio is 1.67. So, some of the typical shape of the other powders like you can see the spherical shaped powders. So, you can see that these spheres, but it shows a more like a bimodal type of distribution. Some of the sphere powder particles is larger size and some of the particle powder size is relatively much smaller size. So, if you plot this particle size distribution, then there can be two kind of a peak. So, and this kind of peaks is called bimodal type of distribution. So, once you do these powder particles, then you have to mix it with other phases, other ceramics or metals, and then you can use the ball mill, and this mill there the powder to ball ratio is typically maintained as 1:4 or more or higher, up to it can go up to 1:10. So, that means if you want to mill 50 gram powder, you must add 200 grams of the ball, so that you can ensure efficient milling of the powders. So, the powder milling has two purposes. One is to reduce the particle size, that means you start with the micron size powder, you expect that at the end of the ball milling you get submicron sized powders, that is the number one. Number two is that in case of, for example, you are adding hydroxyapatite and you are adding to titanium. So, essentially addition of titanium, you have to ensure the titanium is homogeneously mixed with hydroxyapatite. So, that homogeneous mixing also needs to be accomplished, and that places the second importance in case of the powder milling. Now, there is certain thing called limitation. So, as far as the first aspect is concerned, when the crystallite size or powder particle size is reduced, but there is a limit to which it can be reduced to a maximum level. Beyond that, there is not much reduction, and that has been shown here in the case of the alumina particles as a model system. What you see at the end of the 24 hours, the particle size is around 20 to 30 nanometer, and then it remains constant towards the rest of the milling time. Now, after the milling is over, then you have to do compaction, that means you have to take the powders, and after the powders then you have to press compressive force, and these powder particles of void spaces here, this void spaces is squeezed, and then you get a solid compact, and the solid compact you get, and then you call it as a green compact. Why it is called green compact? Because you have not sintered that compact, that means you have not fired them at high temperature, or in other words you have not heat treated them high temperature. At the room temperature it is called green compact. After the green compact, you need to consolidate this compact, and that process is called sintering. So, sintering is the process of firing and consolidation of powders at a temperature T greater than 0.5 Tm. So, somehow you can see that T by Tm greater than 0.5 is something kind of unique temperature, where the earlier bulk metallic deformation processes like rolling, forging, extrusion, all these processes are much more effective at hot working conditions, like when temperature, actual temperature of operation, actual temperature processing is greater than 0.5 Tm. Here again, in the context of the ceramics densification, here again you can see that sintering takes place normally T greater than 0.5 Tm. So, therefore, this is called homologous temperature, like ratio of the application temperature to the melting temperature. So, homologous temperature of 0.5 is kind of very unique, and this has been used in many metal processing, many materials processing techniques. Now, why T greater than 0.5 Tm? Here diffusion and mass transport, that means here diffusion processes becomes much more effective or much more extensive, and that leads to the formation of a dense solid. Now, what is the two different kind of classification? One is called solid state sintering and one is called liquid phase sintering. Now, in case of basic phenomena that which occurs due to the sintering is essentially what I have shown here. This is the spherical powder particles. Now, the spherical powder particles, which this is in the green compact. In the green compact, so this is the powder particles, and these powder particles, this is spherical shaped powders. These spherical shaped powders which will undergo densification, then it gets a hexagonal array of the grains. Now, this is your grain microstructure. Okay. So, in the grain microstructure, whatever you see, the size of these grains, the size of these hexagonal grains has some correlation with the powder particles, but essentially what you see that whatever the void spaces, the way I am sketching in between the interparticle region, these void spaces are lost. That means these void spaces are removed, leading to a very dense grain microstructure. Now, this dense microstructure is characterized by certain geometric shape and size of the grains. So, this is one of the scenario, that is scenario number 1, Another scenario is that scenario number 2 that I have highlighted here. Here densification also takes place, at the same time coarsening also, particle coarsening also takes place. So, if you compare grain number 1 and grain number 2, if the grain size here G1, if the grain size here G2, so G2 is essentially greater than G1. Okay. So, this simply because that here sintering is not done in a correct manner or in the correct temperature for the correct time. So, if it is inappropriate selection of the sintering conditions can lead to grain coarsening. So, this one I have emphasized in this slide. Third scenario is that if you have a very poor understanding of the overall sintering process, then you arbitrarily select the temperature of the sintering, then your this particle size, this simply will undergo coarsening, and then your particle size will increase, but there will be no grain structure formation. So, this is also another important thing in this sintering process. This is a typical sintering curve, like how the densities changes with the sintering temperature. Now, what you notice here that all this curve has a similar qualitative description, like this is a finer particle powders, this is the coarser particle powders, and this is the hot pressing. What is hot pressing? I will come to this in after 5-10 minutes. So, hot pressing is a unique technique where you are applying uniaxial compression pressure when you are heating the powder compact. Now, this is the curve for the conventional sintering. Conventional sintering means you do not apply any pressure, but you are simply heating the powder compact at higher temperature, so that diffusion or mass transport process can take place. So, conventional sintering and hot pressing, in case of hot pressing you are essentially adding additional external pressure to accomplish the densification process. Now, what I would like you to notice here is that during the initial phase of the sintering, the density increases. Then after that intermediate phase of sintering, there is a largest increase in the density. That means maximum density densification take place, or maximum removal of the pores from the powder compact takes place, that is intermediate densification. And the final stage of sintering, then it reaches almost at the final end, and there sintering that consolidation or density change takes place to a much smaller extent. So, this is what has been taking place, that is initial stage, there is a neck formation, intermediate stage there is the interconnected pore formation, and the final stage of densification, that is the closed pore formation. So, initial stage, that is the initial stage, that is density change is almost 3%, and you start with a green body which has a density something around 50 to 55% of the theoretical density. Theoretical density typically in ceramics literature is known as rho Th. Rho is the typical way density is denoted, the subscript Th essentially stands for theoretical density. How it increases in the final stage and goes to the isolated pores, then this in the isolated pores the essentially this one is only 7% change in the density. So, as far as the mechanism of the density is concerned, people use 3 particle model or 4 particle model. In all the theoretical description of the mechanism, I must mention to you a priori is that all the particles are considered as spherical, because spherical particles the geometry is very regular, and then one can also derive certain equation because you have the spherical geometry. And second thing is that in 3 particle model, 4 particle model or 2 particle model, in all these cases the size of this individual powder particle is considered as identical, or they are considered as equal or same. So, essentially all the 3 particles have the identical particle size. Now, coming to this one, there is 3 ways this densification takes place. One is this densification along the grain boundaries, one is from bulk, and then this diffusion process goes to in the neck region. So, this is called bulk diffusion, this is called grain boundary diffusion, and another one is surface diffusion, like it evaporates something and then it comes back to the neck region here. So, this is the 3 type of diffusion processes. One is called bulk diffusion process, the second one is a grain boundary diffusion process GB, and third one is that surface diffusion process. Okay. This is that one more very simplistic description of the process of sintering. You have a 4 particle model, you have this kind of pore space, okay, and this type of pore space you see, and then after sintering now you heat it up, and then what is happening during heating, this pore shape is dynamically changing. It becomes more like off symmetric, and it does not have any uniform geometrical features and so on, and then it will be squeezed slowly. After it is squeezed, then it is completely disappear. So, as the sintering process advances, what happens is that when the pores will not be any more connected to each other, they becomes isolated. Then that particular case, it is very difficult to remove the pores, because I will just give you the 3 examples. One is the pore number 1, one is the another pore number 2, and third one is the pore number 3. Here pore number 1 and pore number 3 are located well within the grain. Pore number 2 are located at the grain boundary region. So, when the pores which are located at the grain boundary region, those pores can be removed very easily, simply because grain boundary diffusion process is much faster than the lattice diffusion process. The pores which are marked as number 1 and number 3, that will be very difficult to be removed, simply because bulk diffusion process is extremely slow. The same has been shown here in this particular figure here. So, this is your one grain, this is your another grain, and this is your third grain, and this is your fourth grain. So, this is one grain, grain number 2, grain number 3, grain number 4. What will happen, because of the curvature effect, grain number 4 will disappear completely, and that will lead to the coalescence of the pores which are located at grain 1 to 4, grain 2, 3, 4, or grain 1, 4, 3, and these pores become larger pores. So, then this will become the new grain number 1, 1 dash, this will become this grain number 2 dash, and this will become new grain number 3 dash. So, certainly the size of grain number 1 dash, if I may write it like this, is greater than grain number 1 before the final stage of densification. The same is true for grain number 2 dash, size is greater than grain number 2. So, essentially what you see during the sintering process is that both the grain growth takes place, at the same time pore growth also takes place. So, grain growth and pore growth, they take that simultaneously takes place during the process of sintering. This is a classic example of the hydroxyapatite microstructure, and what you see is a very fine scale microstructure which is sintered at 1200 degrees Celsius. Now, what I am showing here, this is 1200 degrees Celsius sample, and this is 1400 degrees Celsius. If you compare immediately between these and these, what you see, there is a large grain size and there is a small number of grains also here. So, this is the smaller grain size and this is the much larger grain size. Suddenly the sample sintered at 1400 Celsius would exhibit bimodal size of distribution, whereas sample which is sintered at 1200 Celsius should show more uniform unimodal grain size distribution. And this bimodal grain size distribution is certainly because of the grain growth when the sample is sintered at higher sintering temperature. So, this places the importance of correctly or appropriately selecting the sintering conditions in terms of both temperature and pressure. If you do not have sufficient understanding of the sintering process, and if you arbitrarily or by heat and trial method, if you use the sintering conditions, then what will happen? You may get a dense microstructure, but the expense of the grain growth. In other words, if your sintering temperature is higher, then certain grains will show exaggerated grain growth or abnormal grain growth. Essentially, then you will get a mixed type of population of larger grains together with the smaller grains, and that is not good for mechanical properties. For mechanical properties, your typical microstructure that is required uniform grain size distribution, not like bimodal type of distribution, and also the finer grain size. In the material science, it is well known, the finer is the grain size, better is the mechanical properties. Better mechanical properties meaning hardness, strength properties. Okay? Fracture toughness depends on various other parameters depending on what kind of material you are considering. Now, having given sufficient background on the conventional sintering processes and the sintering mechanisms, let me now spend some time on the advanced sintering processes, and some of these advanced sintering processes has been used to develop many materials both in the lab scale as well as the commercial scale production of the ceramic based materials. And these some of these results also will be shown in the subsequent modules when I will discuss the development of specific materials or specific composites based on hydroxyapatite and so on. So, one of the most advanced sintering processes is called hot isostatic pressing. As the name suggests, hot isostatic pressing essentially means you are applying equal pressure from all directions. Now, the classic example is that this is a typical hot isostatic pressing chamber. So, you fill it up with some high pressurized gas, let us say argon. So, argon, then you pressurize it like 300 megapascal and so on, and then you put your sample somewhere here in a glass container. What will happen when you create this pressure there, and according to Pascal's law, pressure that will be transferred in the fluid will be equal from all directions, right. And if you follow this Pascal's law, then what will happen, that this material will experience the equal pressure from all direction. So, therefore, isostatic, that one is reserved. Hot means this argon gas firing in the, you are firing in the argon gas environment that takes place at high temperature, that is why it is called hot isostatic pressing. What is the advantage between of hot isostatic pressing over the hot pressing? Now, if you look at the hot pressing technique, which I will come to here. So, in the hot pressing you put the ceramic powders, or for that matter of fact any powder particles, then it is a external heating process. So, the heat is coming from outside through inductive heating coil, and their temperature can go up to 1800 to 22,000 degrees Celsius. And then when it becomes red hot, then you also apply compressive pressure here, and when you apply the compressive pressure, it is known as, it is mentioned here 1800 to 2000 psi, that is pounds per square inch. But typically in the commercial hot pressing machine you can go up to 30 to 35 megapascal, okay. That is the typical commercial hot pressing machine. Now, in the commercial hot pressing machine, when you put in the die and it is contained, then because of the constraint that that your material will get densified. But here you are applying the pressure only from the in the compression, uniaxial compression mode. If you go back to the hot isostatic pressing mode, you are applying the pressure from all direction and in equal amount. So, that uniform densification of the sample is possible in case of hot isostatic pressing, which is otherwise not possible in case of hot pressing technique. So, therefore, little bit more details of the hot isostatic pressing. This is the American isostatic press, this is AIP, stands for American isostatic press, who manufactures this kind of hot isostatic pressing. So, essentially the concept that is used, that simultaneous compaction and sintering, and here container is subject to elevated temperature and a very high vacuum to remove air and moisture from powder, and operating conditions like 100 to 200 MPa inert gas like argon, and temperature is got more than 1100 degrees Celsius. This is the classical hot pressing unit. So, you can see this is the ram here, you apply this compressive force, this is your graphite die punch assembly, and you can see this is your punch here which is exposed outside, and inside the die you have a die cavity, and there the die cavity, this powder is now filled up in the die cavity, and this is your die cavity, and then whole assembly is now put it under two upper punch and lower punch, then you apply the compression pressure and then the material gets densified. The last technique before the end of this module is the spark plasma sintering. Now, spark plasma sintering is very similar to that of the hot pressing, but the fundamental difference between spark plasma sintering and hot pressing is that instead of the hot pressing what you have seen, there is external heating. In the spark plasma sintering, that is that you allow the large amount of current to flow through the graphite die punch assembly, and then it goes there, and this is a on off pulse DC generator, and in these graphite plates, that is depending on the conductivity of the sample powder and depending on the conductivity of the graphite die punch assembly, some fraction of the current will go through, and this is a very clear picture, like you can see that powder particles here, and this is the fraction of the current will go through like this, and this fraction of the current will go through, and this is a DC pulse generator. And then after that what will happen, depending on how much current is passing through the powder compact will be heated up. So, this heating is typically done by the Joule's heating, where H is equal to I square R T. I is the current that is flowing through the sample, R is the resistance, that is the contact resistance, and T is the time through which this current is passing through the material. So, because of this high pulse current, now you can see that through this window that how this temperature is shooting up. This is a commercial spark plasma sintering machine, where hydroxyapatite based materials can be routinely consolidated and densified, and then you can do this sintering process, and you can sinter it at even higher temperature to consolidate the material. So, one of the technique here is this Joule's heating, and in the Joule's heating essentially what you see that so, this is the schematic, it shows that this is the 3 particle model. This is the particle 1, this is the particle 2, and this is the particle 3. This is the particle 1, particle 2, particle 3, and this is the contact resistance here. In the contact resistance here, when the current will pass through these particles will experience certain resistance to the current path. Now, this contact resistance will essentially give it as a resistance R, and this current which is going through, that is the current I. So, there the total temperature that will be generated, heat that will be generated is nothing but I square R T, and this is the neck formation that will take place here, and this shows that how this neck formation is taking place, and this neck formation to localized heating is possible. This is the examples that how fine the grain size can be. You can see this error by micron bar here, it is 100 nanometer. So, 100 nanometer means essentially these nanostructured materials can be very easily sintered using the spark plasma sintering machine. So, I think I have now completed that ceramics processing, and this will be followed by some description of the different ceramics of relevance to biomedical applications in one of the future modules, and so that you can understand that how different sintering conditions are to be tailored to develop some materials.